This is a lecture on diffusion models for 3D. So a little bit of an intro. My name is Mitya. I'm a machine learning computer vision guy. I worked on this and I'm an enthusiast of this whole topic. This is a lecture with lots of ideas that I'd like to share that I think are very cool with a little bit of a build-up. I do assume some background. If you are not familiar with computer vision stuff, neural networks, diffusion models, transformers, I may mention some of this stuff, and if you want to dive deep into that, let's do that, because this lecture will be productive only if you interrupt me when something is not clear. We can definitely take detours, discuss different stuff that is relevant to this. I may just interrupt you and go on with the lecture, but I'd like you to occasionally stop me to discuss whatever you think is unclear. Let's go. First, I'd like to discuss the context with you, what this whole thing is about. So, diffusion models. Who has not heard of diffusion models? Who doesn't know what they are? Okay, whatever. Diffusion models are these generative models. You give them whatever description or text, and they give you out the image. For example, these are the two big ones: DALL-E 3 from OpenAI and Midjourney from Midjourney. Both these are galleries of images generated by a neural network. In comes the text, some kind of prompt, out comes the nice image. And to us, more interesting is Stable Diffusion, because most of all of these basically. And what we can work with is Stable Diffusion because it's open source. It's available to you. You can just download it and try it out on your laptop, not via an API. And most of the stuff that I will be discussing with regards to diffusion models is using Stable Diffusion. And most of the research and most of the open source community is using Stable Diffusion. There's also really cool tools that let you use it. So there's a no-code editor tool with nodes that let you set up these pipelines to, for example, one of the things you can do with diffusion models is draw a sketch, and then the diffusion model will use this sketch to draw an image that follows the sketch. And there's this comfy UI program that lets you set up these pipelines that let you get creative in various ways. So, for example, this example is pretty cool. You can do whatever, and this runs all on your laptop. So the context for this lecture is kind of when Stable Diffusion, diffusion models only appeared. There were lots of people that experimented with them, try different prompts, try things for consistency, generate the same character in different poses, in different contexts, because they want original characters and be artsy with it. And one of the things they try to do is have the same character but generate them from different viewpoints. And you can see for these examples, for example, on this life example, it's not very consistent. This back of the shirt doesn't match this, the boots don't match, and so this isn't perfectly consistent. But the idea is that we may want to generate something, not just this one 2D image, but a 3D model that we can then look around, maybe generate a rig for it, so that we can animate it in whatever game or 3D software that we want. And so this approach doesn't work, where we just take this 2D generative network and try to prompt it this character from the front, this character from the side, this character from the back. This doesn't work as well. So we may want to use somehow diffusion models to generate the 3D object, this but in 3D. So it's perfectly consistent. So the very naive idea that we can try is there are lots of already existing approaches that you just give them 2D images of the same object, and they try to give you the 3D model. But the naive idea doesn't work because of this, for example, right? Because each time you query the diffusion model for, a cute cat, it will generate a little bit of a different cute cat, and it will be an amalgamation, this weird crafting creature that you don't want. What you want is an actual cute cat in 3D, not this. We need some ideas to make this work. There's this. So this is an excerpt from a post from Lillian Wang. She is a researcher in OpenAI. She has this blog where she does deep dives on math and machine learning. And if you already know about diffusion models and you want to like understand the scientific backbone of the diffusion models, this may be interesting to you. But this isn't.
What is it? What is it?
This is the backbone for diffusion models, like the math for diffusion models. If you really want to dive deep with it.
Okay.
So like the probabilistic framework, like the Markov chains,
Okay.
all that. But this isn't really relevant if you just want to develop an intuitive approach. I'm saying this because usually when you Google diffusion models, you get something like this, when this isn't like what diffusion models actually are. They're a lot easier, I think, to understand. So like the basic idea, again, this is relevant to diffusion models for 3D. We need to understand how diffusion models actually work. Maybe you've seen like the visualizations of this, maybe not. A diffusion model is a neural network, like one neural network. And the whole point is that in comes like some kind of noise, and over multiple steps, this same neural network denoises it into something that follows like the input prompt. So for example, we have a prompt, I don't know, a cat, and the noise. And then over many steps, here it's 4 steps, but usually it's like 100 steps. This noise slowly becomes, via this diffusion model, this image.
Can I ask a question?
Sure.
Is this deterministic?
Well, at least it's not, because like there's a seed in the input.
If you provide the same seed multiple times, will the outcome be the same?
Depends on the implementation. So usually in every implementation, there's like a coefficient onto how much randomness you want. So depends basically.
Is it also conditioned on the cat thing somehow? Or?
Yeah. So sorry, like you can train the diffusion model like without any text, just so that it tries to denoise. But then like it's very chaotic. You give it noise, and it doesn't know what to denoise, so you get like some weird output. The whole point, like why diffusion models blew up, is that you can put in this noise and the text. So for example, like a cat, that it will denoise towards a cat. Now, yeah, the whole point is like let's try to understand like what this neural network actually does, because this is like the overall pipeline for generation. But we need to understand the spider. Holy shit! Hi, spider. Let's try to understand like what is actually the input of the diffusion model and what is the output. So this is like, again, the basic idea is that we have a noisy image. It's not like fully noisy yet. It's like an image with some level of noise. Let's say that this level of noise is T. Like it's an interpolation between an image and pure noise with level T. And our model is trained to like predict the noise exactly. So that if we remove this noise from the image, then out comes the perfect image. So like the diffusion model is basically literally a denoiser. It's learned, trained to predict the noise in one step, not like predict the next image. So, but this doesn't tell us why like it can generate over multiple steps. So what it does is we give it this image and some kind of T that describes the noise level in this image. It gives us like the noise, but instead of subtracting all the noise to get the denoise version, we subtract just a little bit of that noise to get like this a little bit of a denoise version. So we get the noise, but instead of like denoising fully, we get a little bit denoise basically. In practice, this shows that basically if we do this over multiple steps, it's a lot better than just doing like this one denoising step. The more denoising steps we do, the better. And the whole point is that we train the diffusion model basically like this. We have an image, we add noise, and we train it to predict the noise properly. And we train it like this, and even though it's trained like on a pretty simple task, it can do this multi-step generation.
Why the picture is...
Sorry, it's backwards because usually diffusion models are described as like you noise the image, which is the forward process, and then the backward process is the neural network tries to denoise it. So sorry, this is like a little bit confusing direction, but the point is like during training we have images, we add noise to them, and then the neural network is trying to do the backward thing, denoise them.
Is it good at if you prompt a noisy picture, is it good at generating noise?
That's an experiment. I'm not sure. Basically, it's trained on like a huge data set of high quality images from like stock photos. I doubt that it's has an understanding of what like the perfect noise image is, but I'm not sure. Maybe it's.
Noise is it's deterministic kind of, I think, because we have artificial. It's not a fully random noise. It's just pre-calculated some function.
The question was if we like we have prompt like please generate me a noise image. Will it be able to like would this generate a noise image? This same thing. I'm pretty sure not. It's too confusing. So now, okay, so there's this all confusing math that you'll see in the original diffusion paper, DTPM, denoising diffusion probabilistic models. And I'll try to like demystify it because it looks pretty hard, but it actually isn't. So this is like a conditional distribution. Like, what does X is an image, and so what does an image with noise level T look like with regards to like the 0 level noise image? So X0 is the image itself because it doesn't have any noise. It's noise level 0. So it's distributed like this. This is just a normal distribution. You can decompose it like this, basically. Point is, like this image with noise level T is just an interpolation between the image and the noise. Like, this literally is a formula for combining an image and noise. This is basically how easier to describe it. If you want to get an image that is noise with level T, it's an interpolation between the pure image and the noise with like coefficient T. Whole point. Okay, so this is how we add noise to an image. Now, now that we have this noise image, our model is like a function which is our model. This is its weights. Usually how it's the notation for weights of a neural network. It's given this image with this kind of noise and the level of noise. This isn't the noise itself. It's like this coefficient, just one single value. And the point of the network is that it's trying to predict noise, and the loss function with which we train the neural network is just the difference between this predicted noise and the noise that we use here. So this is again literally how we train this diffusion model. Sorry, I didn't ask. Like, are you familiar with neural networks? Should I describe basically how what this loss does then?
What does?
What this loss function does. So we defined it. This is what we want to minimize, right? If our model is very good at estimating noise, sorry, this hat is usually the notation for like estimation. There's the true noise that we added, and there's this estimation of the noise. And we want these two to match, so we want to minimize this loss function difference between the true noise and our estimated noise. And so we do gradient descent, this whole thing in machine learning, that changes the model weights until this is like as small as possible. And so in the end, we have the model that perfectly predicts this noise. And if we perfectly predict the noise, we have a perfect denoiser. And if we have a perfect denoiser, we can do this.
During the training, will it compare the original image with the noised original image with the noise? I don't know how to explain it. So during the training, you have the original cat image.
Yes.
But you add some noise to it.
Add noise.
And after the neural network denoises this image, will it compare the new denoised image with the original?
Yes, so that's kind of the point. So it's basically here I say that we compare the noise and the estimation of the noise, but this is basically equal. We can rewrite this as like comparison between the image and the denoised image. So you can use this noise to like generate the denoised version, and you compare like this denoised version of the image with the pure image. Okay, and they should be like as close as possible. Yeah. So like minimizing the difference between these noises is the same as minimizing the difference between like the original image and the denoised image.
Can I ask a question on previous slide?
Previous slide. This one.
Yes. Why you have in three parameters into a normal distribution? So
So you can see that there's like the semicolon and there's a comma.
And so it's this comma.
Yeah. So this is the parameters of the normal distribution. So this is the mean, and this is the variance. This is just like the argument. So we take the distribution of these parameters, and we get the probability density at this point.
Okay.
And this is the value of this like conditional distribution.
So basically, we train, we get a lot of pictures which are marked, labeled with cat, dog,
Yes,
tree,
yes.
and some other. And then we add noise and train the model to identify what is equivalent, what is not noise in comparison to the label. So it's
kind of
like in a negative, in a positive and negative photo image, right? So noise is something what we would like to deduct. So we approximate or extrapolate what is not noise in the picture. So
Yes, kind of.
we understand having the label, we understand what is in the noise is not required, what we need to eliminate.
Yes, that's a great point that I forgot to mention. So all of this here, this looked like the initial paper for diffusion models. They didn't have any text prompts. They only trained the model to denoise. And then like later works that blew up with the diffusion models, they used prompts here. So this model did not only take the image and the noise level, it also took a prompt.
So the original intent of this work was to make a neural network that will denoise any picture.
So it's the original purpose was still to like generate images, but this was like they didn't understand that if you also condition it on text, you can improve the quality. They thought that, like just pass in this noise and it will generate a random picture for you. They didn't control what picture it generated; it just generated a random picture for you.
But if this noise was like the second from the right picture, like something like a cat, it would probably generate a cat.
Yeah, kind of. They also tried like generating noise, and then it would generate a completely random. But if they gave it like something like a cat that is noise, then yeah, it would be likely to generate a cat that looks like that.
Mhm.
Maybe like a little bit different. Maybe it would be different colored cat. So in that way, it's pretty random because over multiple steps, it can generate something different depending on the scene, basically.
And also, this neural networks is invertible somehow. So its special architecture is used, so
No,
you
no,
can
no.
invert it.
This particular architecture is not convertible. So for example, if you take this cat, you add noise to it to get this image, and then you apply a diffusion model to denoise it back here, then you will likely get different images. And when you basically like the current architecture is used for diffusion models, they are not invertible. Like very likely, if you try to do like a backward-forward process, you will have a little bit of a difference.
So am I right that you say that we are training a model at first from left to right, and then we reverting it and then getting from right to left?
No. The model is trained like this particular function. When I say that there's a forward process, this forward process is just a function that we apply during training. So again, we have this pure image. The forward process is we just like manually add some noise to the image.
Okay.
And
Okay,
some others
okay.
at different levels.
Yeah, no, like during training with sample.
Just some slide from a previous some previous slide, just a little bit confusing.
Which one?
Yes, this one. So diffusion model is just doing backwards.
Yeah, kind of. So
Why we here have a box that named diffusion model? It's just not diffusion model, just summation.
No. This is like you can't like this info isn't
Yeah,
enough
we
to-
just adding this to this picture with the noise and getting the right.
No,
and then
this is the noise image. Like you need a neural network to predict from these two the noise. So there is no formula.
it is another model. Or you invert it.
No. This is what I'm talking about. We have the
But we're
noise.
doing this backwards.
Noise level is a scale one. It's like 0.5. You can't
Yeah, this is a noise. This is just one value. Like for example, 0.5. Right? Well, like we don't have noise. here. This is just 0.5. So we took this. 1 second. We took this image and we took this noise. We interpolated them with this level. So alpha t is basically like some kind of, I don't know, this curve, right? For example, we have t equal 0.5, and alpha t is like some value here. Like different implementations have different curves like this.
Ah, okay. You can
That's
choose. You can choose any parameter.
It's called a schedule that you'll see in the literature. Point is that this is just a value, and t is just like one single value.
Ah, okay.
So here as input we don't have the noise. We have this single value,
Ah, okay.
and we want to predict the noise.
Hmm.
And somewhere here afterwards, I want to like important note. Researchers intentionally complicate math to look smarter. When you look at papers, you can see this, and most likely you don't need to understand this. There's like a lot easier way to understand this whole thing. Like try to develop some kind of intuition without
Can
thinking about
we make an image-to-image model which takes this kind of information without simple math?
Yeah, that's for research. I sometimes use like GPT-4 to I give an image and please describe this to me in baby terms. Well, after we train the network, we can generate this image over multiple steps, like doing this slow process of denoising. And I guess I forgot to add. One sec. Yeah, I forgot to add something. Yeah, basically the point is that the modern diffusion models that you'll work with have here an additional arrow like this prompt, basically. Like here it only denoises the image, just the image basically with this noise level. But in practice right now, when you have a diffusion model, it also takes in the prompt, and so it will try to like denoise towards the prompt. So that if you have a purely noisy image, this noise level and the prompt, it will try to, for example, like, generate a noise that would generate it towards the cat.
Is prompt generated by another neural network?
You can just input like the whole point is that like you just type like a cat, and this text a cat will be encoded into something that this neural network can take in. The diffusion model every time in these steps it will take in the image, the noise level, and the prompt a cat, and this way it will slowly denoise into a cat. And if I input something like, I don't know, a truck, then from this noise, from the same noise, it will denoise towards the truck. Okay?
Is noise always the same, or it is randomly generated?
Oh yeah, it's so every time you run this model, the noise is randomly generated, so that every time you get a different output. But as like, sorry, what's your name?
Team.
Team.
Yeah.
Okay. Sorry. As Tim said, like you can feed the same noise into the model, and depending on the implementation, you either get like the same output or maybe a little bit of a different output. And so you can experiment with that. Yes. Okay. Now towards. So this is still important to 3D. Sorry, this is like a lengthy introduction because this is relevant to like how to generate 3D objects. So like this very trivial idea that we can use to like edit images with diffusion models. We trained them to denoise. We used them initially for generating images from text. But now imagine we just give it this like very weird sketch, very blurry or like sketch. You add noise to it, but as you said, like such that an image is somewhere seen here. Like you can kind of make out there's some kind of castle or not. You can kind of make out the structure of the image just looking at it. And so the diffusion model from this denoises towards like something that makes more sense, right? So this is like the very basic idea. Don't look at these like this thing on the top. This is like some intuitive stuff that I don't want to discuss right now. Point is, you have like an image, you add noise to it, and from that noise you like slowly denoise, and you can get a different image.
What is strobe here?
So the stroke it means like a sketch. So if you grab sketch, like this isn't an image, you just I don't know, hand drawn something colors.
And what do these things represent on top?
On top, so this are like kind of distributions. So point is, you have this distribution of images and you have distribution of like these strokes. And when you add noise, these distributions look very similar. So if you add noise to sketch images and if you add noise to realistic images, they look basically kind of the same. And then when you denoise, but you train the model on real images. If you denoise, this image will go towards real images. So even though in comes this sketch image, out comes a real image, something that looks like a real image. And another idea is that you can give it this image and then use some kind of other prompt, cyberpunk castle, and it will denoise towards a cyberpunk castle using this sketch. Like this is the basic idea that you can use.
It makes sense actually, because in the original image, the narrow points, dots, are somehow related because your brush makes a continuous stroke. And so when you add the noise, you make this picture blurred, and the adjacent points are not related. So then when it denoises, it makes another image which is more realistic. But otherwise, the first image would also be considered realistic for the initial, for the diffusion model, because the strokes are continuous. So what the model does is it takes blurred image and makes it like continuous, extrapolated.
Well, I think it's not blurred. Maybe it would be a good technique for further neural network development to actually blur images, because adding noise does not blur borders between different colors. It just adds randomness between each pixel. But maybe if you blur the images, it may generate even more realistic results. It's just my thought. Or maybe if you add like random pixel shifts to any direction.
There was research that like instead of adding noise, it tried different like perturbations, for example, like blurring or masking random places. So yeah, there was research towards that, but that doesn't work as well. But that's about maybe.
So it worked, but not so popular.
Not like this is a lot better to work with because there is a mathematical backbone that makes more sense. Whereas blurring doesn't work as well because it's harder to tweak in some places. But there is a paper that makes that work. So you can train the diffusion model, but instead of adding noise, you blur like in different ways. Okay. And then the smaller tries to deblur. But like that's like a different line of research. So yeah, is this idea kind of clear? Yep. Nice. And there is also like a way that you can instead of that idea, you can fine-tune a model for the task of editing. So, for example, you can use some other approaches, like let's not discuss it right now, that generate paired images with the same structure, but like a little bit difference in content. For example, this girl on a horse and this girl on a dragon. So there's a different approach that can do that. Sorry, I won't dive too deep into it right now. Let's assume that we can do this, and we have prompts for both. And then we can fine-tune a model to not only like generate an image given a prompt and this noise image, we can also give it like this conditional image. For example, it takes in, let's jump actually. Before we had like this input image, T, like image with noise T, level T, which is like the noise level. We had the prompt. All of this was fed into the model. Out comes the noise. But we can take this model, this neural network, and there are lots of different ways that we can fine-tune it, like train it to do something additional without changing its knowledge too much. What we can do is an additional input is like conditional image. So now we still generate images from scratch like that cat, like this noisy image, then multiple steps. a cat. But during this process, we don't not only we feed the noised image, the level, and the prompt. We also feed like a conditional image that we want the resulting image look like this conditional image. So point is, we can do generation from scratch. This image is generated from scratch using the prompt, like some kind of prompt. But we feed this as like a condition during the generation process, like an additional input to the neural network. And this forces this resulting image to look a lot like this initial image.
It is trained from scratch, or
No.
somehow it is used result from previous learning.
It's not trained from scratch, so we already have this diffusion model
Okay.
that is already trained very well. And again, this is stable diffusion. So stable diffusion has these inputs, and then we add like a module from the side that also feeds this input. And we fine tune this model, like not from scratch. We take the weights of it and then we change it a little bit such that it now learns to use this conditional image.
Interesting.
After we fine tune it, and for like our data set for fine tuning is this. So we know that if we generate this image, it should kind of look like this, and it's this way it learns that when it generates an image, it should kind of look like the conditional image. So now we have like this approach that takes in an image and an instruction, and then like it is pretty good at following this instruction. Again, this is like a high level overview. You can read the paper and understand it a little bit deeper. Now we can finally go to 3D generation. So like about the 3D generation, first we need to discuss like what kind of 3D objects are there, 3D representations, because there are all kinds of 3D objects and there are different ways that we can represent them in like in computers. So the most
previous slide, sorry.
previous slide.
So the prompt is turn her into a snake lady, right?
Yes.
So how does the model work? Does it first try to describe the initial picture in words, and then uses this prompt to alternate it a little bit, and then reiterate another image with a slightly adjusted prompt?
Yeah, so I don't remember particularly, but so it's one of two things. So they already say that they use GPT-3 for this training to generate, like if they have this input, one data set that we can think of, one like instruction, is that there's this other prompt, and this is the instruction that would have gotten us to this prompt. So if we have like a girl riding a horse, then one possible thing we can train on is like this instruction, have her ride a dragon, and like the target prompt. And pretty sure during training they also like have they encode this and they fine tune it to already fine tuned it to take in these instructions.
So new instruction.
Yeah. Okay. Cool. So about 3D representations, like in 99% of cases, when you work with computer graphics, when you work with game dev, when you work with anything 3D, they have these kinds of models. It's a 3D model that is represented with like these triangles. Almost every 3D object can be just decomposed into its surface, can be decomposed into triangles. And this is used like almost every time. What can also be and sometimes is used in computer vision as like this representation for 3D objects is a point cloud. So this is like you can probably see that this is just a lot of points in 3D, and if you color them, then they can actually start looking like an object if you visualize it. And it's like even though it's very missing some parts and places, it's still used sometimes in computer vision just for context. Now, like again, my favorite topic, nerves. This is another thing. A newer, like very modern way of representing 3D objects. So I'm going to describe how it works because it's very much based on machine learning. So my favorite slide. Point is like before a lecture I was talking about 3D reconstruction. It's like this this problem where you have many photos of an object, and you want to get the 3D model of the object. There was like this older science called photogrammetry that did this with like older, more classical computer vision approaches. So you give it images, and then it reconstructs the 3D model of the object in the images. But then now there's this way that does this, but using machine learning and a neural network. So the idea is, assume like, for example, this Lego truck. Assume you have this function that, given a position of a point, like in space of this truck. So for example, inside of this truck, on top of this truck, whatever, like just a 3D point, a position of 3D point, and the direction of views. For example, there's this Lego truck. I look at it from this direction. This is the spherical coordinates of a vector. And they are fed into this function, and this function on the output gives the RGB the color of this point. So for example, on this part of the truck, the color is yellow. On this part of the truck, it's black. So if I had a point here, the function would give me black. If I had a point here, the function would give me yellow. And also the density of the material at that point. So for example, if I have a point inside the truck, so inside, for example, this part, then it would give a density of 1. Because this is dense, like light doesn't pass through this point, or it's dense basically. If I have a point somewhere here in the air, then the density would be 0 because it's air, like light passes through, anything passes through. So this is a helpful just intuition, because this density means like the density at a particular point. And if we have this function, then we have something called volume rendering, and I think it's pretty intuitive, but let's try to understand how it works. So if we have a ray passing through some point, and we want to, like, if our eye is looking in this direction, what color would we see, right? If we look using this ray, we can get a lot of points on this ray, use this function to generate the color and density for each point on this ray, and then just sum these up in like some kind of smart way to get the color for this ray, right? And so if we have this function, and if we know how to render a ray, then we can render an image, right? Because each pixel in the image is just this ray shot through this pixel. We can generate the color of this ray using this function on all these points. And so if we have this function, then we can render the truck from here, from wherever you want. And the whole idea is that, okay, if we have this function, then we can render it. And the important thing to understand is that this procedure for getting the color is differentiable. So, which means that if we have images and we want to somehow propagate gradients, and we should like do gradient descent with respect to these images, compute the difference between like an expected color and the color that we get, then we can train this function. So this function will be a neural network that we will train to like represent this truck. So initially we only have images, and then we slowly using gradient descent, this function will become this truck, because we will train it such that these renders match our input images. This is like the point of NERF, my favorite thing.
But still, we need photos from different sides, right?
Yeah, we need like lots of different photos from different sides, and using these different photos from different sides, we can like compare the render that we get from this function and the true image, and by minimizing the difference between them. So the loss is literally just the difference between the render that we get using the summation and the true color. If we minimize this difference, then in the end, this function will like look like this, basically.
Yeah, a few additions. I think it has to take into account lens correction, lens distortion of the camera.
Fair enough.
And probably if you use a video source, that you have a prediction model for camera position and direction.
Yeah, so yeah, this is important. So in order for this to work, we need in advance to know the positions of the cameras and their point of view, basically. And right now in practice, this uses like another computer vision algorithm. It's pretty old, like in the 2000s, there was already an algorithm that given images can give out the positions of cameras. I actually had a lecture on that, like 2 weeks ago, 3 weeks ago, I had a lecture on camera pose estimation. Yeah, there are computer vision algorithms that let you estimate the camera positions. And if you have the camera positions and you have the images, you can do this whole procedure and compute the loss and minimize this loss. And if you minimize this loss, then this function will become the true track. So it will truly, at this point, give the color yellow and density 1. At this point, it will give density 0, and so on.
How it is different from cloud of points on the left? How it is different from cloud of points on the left? Do we still predict the cloud of points, or we are already working with triangles here?
None of the above.
Yeah, so the point was that these are like two different kinds of models. This is completely different. So it's not a mesh, it's not triangles, it's not a point cloud, it's this neural network.
At left, it's a picture. At right, it is a field. It's basically a field of objects somehow represented by ray tracing. It's not a point. It's something new. It's this one.
So one thing that I can.
At the right, it is a parametric model.
Yeah, this is like.
It's like a LLM or something. Like
it's an LLM.
Like a matrix.
It's a special neural network
Yes.
that we train specifically for this truck. So
Yeah.
we train this particular neural network specifically for it to give correct RGB and sigma for every point on this truck.
So the track does not exist in any card or something, but this model is used to predict a certain image if we provide an angle of shooting and direction.
Yes. So this is like when I say here implicit representation, this is kind of what we mean. So point clouds and meshes are explicit representations because we have these like point positions, we have vertex positions, and we have faces. This is very explicit. We can position this in 3D space. Whereas this neural network itself, it doesn't have like, it is not described by 3D positions. It's described as a function that if we give it a 3D position and a direction, it will give us the RGB and sigma.
So it's a predictive model.
It's a predictive
model, and this is predictive. So
it's novel view. It can create novel views. Yes, it's predicting new directions.
So if you didn't have a photo from this particular direction, but after you feed this existing images to this neural network, you can then take a picture from the direction that wasn't originally there.
Yes.
So
this is literally how we train this network. So again, we need a loss function to minimize in order to train this network. And the way we do this, we have this true input image, and we have the input image we generate with a network using these like ray sampling techniques. And then the thing that we want to minimize is like the difference between the rendered image and the true image. And so after we minimize this enough, our nerf will be trained and we can get views from new angles and like convert this into, we can then, after we have this nerf, convert this into a mesh or a point cloud or whatever. Not that hard.
So does it mean that all the photos that we have, we split into train and test or something?
We can do that, but we don't need to because the more photos we use, the better. So during like the evaluation of a particular nerf variation, we would get some test images to test on. But hopefully we get as many images as possible. So the naive idea behind generating 3D models with diffusion is that we know how to get a 3D model like a nerf that's kind of a 3D model from images. Then why not just generate something with diffusion? Like these images that we'll train with will be generated with diffusion. We will train a nerf on those images, and therefore we will have a 3D object that was kind of like generated with diffusion, basically, like with these AI models. And so this is the naive idea, like the basic idea, but we'll iterate upon it to try to improve and such that it actually works. So I already had this live. So if we do just that, then we will get this. If we're trying to just train on diffusion generations, because they will be different from viewpoints, but not consistent with each other, and we'll get this weird creature. What we can actually do is, this is like a basic example that I hope will be clear enough. So assume that we have like a nerf, but it isn't very well trained, it's very blurry, and if we generate images, like the images on the output will be very blurry. It's not perfect yet. then we can use our diffusion model to add noise and then denoise. And then we assume that if we denoise with our diffusion model, it's very good at denoising. And so it will get us a better version of this picture, right?
Wow.
Yeah.
Cool idea.
Well, yeah. So we have this image. We want to improve it with the diffusion model towards our prompt. So we have this. We add noise, denoise it with this prompt, and so we get a better version of this image. And this we use for training. So we already have our render. We have an improved version of the render, and what we want to minimize is the difference between this and that. So we want this render to become the improved version.
I didn't really understand this. Is this a real nerf model?
So this is a nerf.
Real, taken from a real picture of a real object.
Okay, assume that we somehow, like, we already have a nerf, but it's trained like this. Like
Okay,
it's,
badly trained.
badly
poorly
trained
trained.
nerf. Poorly
Yeah.
trained nerf. Like, assume.
Okay.
Later on, I'll explain like how we could get here. Assume we have this, and it generates very poor renders. We get this poor render. We improve it with our diffusion model by noising and denoising.
Yeah.
And what we want to minimize is we want this to become this. So our loss function is the difference between this and this.
Okay.
And we minimize this, basically.
And where will we use this training? What will we use this training for?
So what we use the training for is, like here I say we assume that we already have a nerf, but what we can actually do is just initialize a random nerf, so a random neural network, and then do the same procedure. First, we won't have any blurry renders, or we'll have just random renders, just some random image. We will use our diffusion model to improve it towards this prompt. So we'll have a random render here. We'll add noise to it and then denoise towards the Lego truck. This random render will look a little bit more like a Lego truck. And then we compute this loss function. And so if we do this over many iterations, over many viewpoints, slowly our renders will become more and more like a Lego truck, right?
So we will change the weights of the diffusion of the nerf.
Yes.
model.
So our nerf will be updated such that its renders will look more like a Lego truck.
Can we say that we just doesn't have enough photos from different views, and we
No, we don't have
generated
photos.
something,
So
and
right
then
now,
adding another point of view?
this is a different idea. Right now I'm talking about like if we don't have any images, we only have our text. So we only have a text, we don't have any images. We want to create a Lego truck just from text. And so we have this like random nerf, and we have many viewpoints.
Yeah, but this representation also fits to whole pipeline. So
Yeah. So your idea,
Yeah,
in the
yeah.
lecture I have like
Yeah.
idea. Yeah. This
yeah.
what you said can be used. But the idea is that we can have something like a random nerf. We can have a random nerf, and then if we use this, if the renders of the nerf will become more like the prompt Lego truck, then the 3D model itself will become more like a Lego truck. And so if we do this over many iterations, we from something a random initialization, we get a Lego truck in the end. So something's unclear?
Yeah. This is one more thing. So I guess the human mind works like that. We have a certain concept of a four-legged chair, and then we have just one look at the chair from one angle, and then we have a skin, like we have a mesh, and then we have a skin, and then combining.
What do you mean by skin?
Skin, like so you can have a rig of a general head
Okay.
of a character,
Sure.
and then you have a skin. So the color of eyes, the
Sure, okay.
the hair, and
Mhm.
others. So the picture on the left of the truck would be like a certain skin, and a
So
certain
it
concept.
It can be
of,
changed. It can change
visualization.
colors, for example. Yes.
Yeah, it can change colors. It could be like more rubber look like, or more plastic look like, or something. And then we have also a 3D generalized model of the truck.
Mhm.
And then this general model, let's say black and white model of the truck, could be colorized and rubberized.
Yes.
or plastic
Actually,
white.
I have a link in the end of the lecture about how if we already have a model, we can use a diffusion model to generate the textures for that model.
Mhm.
So we have a black and white model, and we can use a diffusion model to generate the colors for the model. So this is another thing we can do if we already have an earth or a mesh. So actually, we can replace this earth with a mesh, but it's not like it won't be as flexible. What we can do is we get the render. It will be black and white, or it doesn't have any texture. We ask the model to please denoise this towards a Lego truck or whatever the prompt is, and it will generate the colors. And then if we minimize this, then the 3D model will start to get colors. Yes. So do you have any?
Well, I just don't understand how you, based on this denoise process, how do we change the initial neural network that generates nerve?
So yeah. So for example, do you understand like why we want to minimize this?
Minimize difference between initial blurry image and denoise.
Yes.
Yeah, I understand.
So we want to minimize this. Now we want to minimize this by like changing the nerf weights, right?
So will it change it randomly, and in case it improves, it will save it?
That is like the reinforcement learning way, or no? What we do is we have this loss. This image, like the render, this uses a neural network, and because this process, the render process, is differentiable, and so if we want, so for example, the gradient descent, the way it works is let me.
Oh, it's a back propagation.
Yeah. So loss is like m minus m. This is the render. So the render is like
This is loss function.
image is like sum of cost this functions. Somehow, like assume this is this. So basically, like our render is a combination of outputs of this function, like x, y, z, da da da. Right? And so this render, it's some kind of combination of colors from our neural network, right?
The blurry render.
The blurry thing, yeah.
Okay.
This is our render, the thing that we get from the neural network, and this is differentiable with respect to to this. So in order to minimize this, we need to minimize the difference between these two. And then this gradient, like the gradient of this loss function, via gradient descent, can be propagated towards the weights of the nerve model.
But will it affect different angles?
So in practice, we do this thing, but in a batch with different viewpoints. So from different viewpoints, this thing will be minimized. The gradient of this loss will be propagated towards the truck, towards the model, and this model will, from different viewpoints, start to look more and more like a Lego truck.
Okay. Somehow understand.
Okay, nice. I hope. I hope this is like a good, somewhat intuition. Let's go further. Yeah. So this is like the screenshot of the diagram from the original paper that suggested this approach. So this is the paper called DreamFusion. This is the main diagram that describes basically the same thing. So they have like a peacock. If you have a peacock, you get the render from this peacock. So this is an Earth too. You get this render. They add noise. They use the diffusion model, which is the UNet, but this is like just basically a neural network that is this diffusion model with this prompt, such that we want to look more like a DSLR photo of a peacock on a surfboard. It will generate us like this, something that looks more like a peacock on a surfboard. And then this difference, basically, we're trying to compute the loss function. This is like a hard thing to explain. They don't do a very good job of it in the paper. But basically, the difference between this and the render is propagated onto the nerve weights. So I wanted to explain it like this diagram in the initial paper is a little bit confusing, but the previous slides.
And when you adjust these weights, the same angle will produce the result that looks more like the
Yes.
approved image.
Yes. So yeah, I wanted to give like an intuition behind this process, and we can look at the results of this paper. Nope, the results of this paper. So all of these were generated with this procedure that I explained to you. So we get diffusion models, we, from different viewpoints, we ask them to look more like a particular prompt.
Where did the original nerf come from?
So the original paper for Nerf?
The original nerf that produces bad images. Is it?
Oh, so we
real
initialize it randomly. So yeah, it's the initial nerf that we use in all of this. It's a random neural network that is initialized randomly.
Okay.
And so for each of these, we initialize from a random neural network. Then we improve it towards like a prompt that we select. So maybe the examples of prompts. Yeah, like here. So this is a prompt. Using a prompt please log for the squirrel, we get this. If we have like a kimono, it will generate this. And so on. So this is a nerf. And right now, like nerf is this like black box, right? But there are methods for extracting a mesh from nerf. So we have this nerf, and then we can feed this into this algorithm for extracting a mesh, and we can get the mesh of this squirrel in a kimono.
Whenever you press a button, it's already pre-computed, right?
Yeah, and this website they just preloaded these videos.
So how, like, what are now? How long does it take, or like what computation?
How long does it take to generate this?
For a single
For some
prompt?
prompt.
Yeah.
So depends on the implementation. So this paper, I experimented with it. I don't have visuals, or I don't have visuals. I'm not sure. So this particular thing takes a few hours to generate, and it's a slow process. But
So you, in the beginning, you have a blank neural network that will generate noisy nerf.
Noisy
nerf. And also you have a diffusion model that can generate images normally. That's a real working model.
Mhm.
And you just run this generation process, and over time it changes the weights of the network that will generate nerf, and in the end you get something like that.
Exactly. Yeah. And yeah, there are examples like chopping vegetables. So these are cherry picked examples. I will show that usually you won't get something this nice. Oh la la, for this, and evil. So, yeah, and they can export meshes. These are not compatible. But you can these are generated, and then you can load this 3D model and use this.
Why approach is good, but the picture is not so good? Why?
Because I'll explain some of the issue.
We will have another approach. Yes?
I think
I'll
it's
explain
just
one more.
the size of neural network. Maybe if you use a larger neural network that takes more computation power, the result will be better.
I'll explain one main thing that lets us improve upon this. And so there's so the code for this is not open source, but there's an open source version that works. And you can actually experiment with this. So this is a little bit different from the implementation of paper. Basically, they use almost all the same, and they get these results. And this is a code that you can actually run on your computer and try to generate stuff. And I experimented with this, and let me see whether. I don't know. I forgot to change the text, but this is my experiment. I tried the DreamFusion paper to generate a frog, and this is what I got. So this is kind of the same issue that I showed with these two images of a cat, because usually when you use diffusion models to generate 2D images, they generate the frog from the front. And so from all of these viewpoints, it tries to generate a frog from the front, and so every side of the frog is the front side. So you get this.
Can you condition that on I don't know, angle, kind of I'm looking at it from the
Yes,
left?
yes, you
right?
actually do, but it's not enough.
Okay.
And I will show the next couple of slides is how to improve upon that and actually get to better stuff. What?
Я тоже игралась с AI 3D, и все эти модели, они упакованы. Для рендера еще пойдет, но при импорте в движки выдают ошибки. Просто страшная сетка, невозможно использовать. Как думаешь, сколько времени еще понадобится, чтобы модели сразу же в хорошем качестве получались?
I'll answer in English, don't mind. There are already, so it does take some cherry picking and prompt engineering until you get the result that you want. And then there are different algorithms for extracting meshes from these. So, for example, this is already an extracted mesh, right? And usually when you generate with the DreamFusion paper that I described, sometimes you get worse meshes, like you said. But there are ways, like this, for example, I used a little bit of a different variation that has a good exporting capability. you can use all the same algorithms, but in a way that exports better. And so, in terms of like when in production this will be usable, I think depends on the demand.
Yeah,
Sure.
it's that work of retopology. Like we can make a neural network that will generate a good mesh out of any image or out of any 3D model that looks like that. So I think there's there's no a good retopology neural network yet. So it has to be made by something.
Yeah, so I guess that right now this is a good tool for like generating references. So you have this like nerve generated reference in 3D, but you have to retopologize and do like all this by yourself afterwards as post processing. So there will be a couple more slides. After that, let's discuss like whether this can be useful in practice.
And you prompted Hypno thought, yes?
Yes, exactly. So following works. Like I'll describe one main idea that lets us improve upon the results that we had before. They looked cool, but not enough. So not meta, I think. Yeah, like some startup like collected from the internet this like very huge 10 million plus data set of 3D objects, which are just meshes that are pretty detailed, high quality, and stuff like that. And so this data set we can use somehow to improve the quality of our diffusion models specifically for 3D generation. So what we can do is like this is like a quick description of the idea. Basically, before we fed like this single viewpoint into the neural network and asked it to be more like the we asked it to be more like our prompt, but now we reconfigure our diffusion model so that it takes 4 images at once from fixed viewpoints and ask it to be guided more towards our prompt. For example, this is a prompt a robot fighter. We reconfigure it so that it takes 4 images at once and generates like these denoisings for 4 images at once, right? We have this huge data set of 3D models, and for these 3D models, we can generate the ground truth for renders from 4 different sides, right? We can fine tune like our model, our diffusion model, to work better on this huge data set, right? To denoise specifically 4 renders at once. And so if we denoise 4 renders at once, we get this paper that gives incredible results, I mean, compared to the initial one. So they even show the process of the generation. Cool. So it's a lot more consistent, and I don't think they open source the code, but I believe a lot more that now they have these like 4 fixed viewpoints from which they diffuse. So they won't have this problems with multiple heads, because now like the diffusion model that will know from the data set that only one of these 4 cameras is looking at front, so it won't have these issues.
But this is not a 3D, it's also a nerve.
This is a nerve, but again, this is pretty easy to extract a mesh from. If you use like proper tuning, there are some hyperparameters to get the proper
But without a good topology.
Without good topology, yes. I don't know. I'm pretty sure there should be tools to improve topology of these exports, but I'm not sure.
Yeah.
It's interesting to connect this with what Tesla is doing.
But what?
It's interesting to connect it with what Tesla is doing. So Tesla gives an image with 8 cameras. If you so here we have 4 images, and Tesla has 8.
Oh, you mean like this is the data set for fine tuning?
Yeah. So and the car looks outside, and then if we reverse it, then we have 8 images of a single object from different.
Yeah, fair enough. So if we have when we have very large data sets of these like multi-view views, we can fine tune that and get better results of these models. Yeah, these are good results. Again, I'm pretty sure they are cherry picked. In truth, the model like needs tweaking, but still, this is pretty great. Like this. So this is a very active line of research. I didn't read it that actively for like 2 months now, but you can definitely read a lot more. There are a lot more papers now.
what's happening with Ace, Luffy, Luffy from One Piece? What's happening with his guy?
I mean, yeah, it should happen. So, there's also like I didn't have it in the presentation. There's also this. You probably may have heard of Gaussian splatting. It's like a different approach because Gaussian splatting is like it's easier to optimize than nerf. Generating with this instead of hours takes minutes. And they use it for image to 3D. So we can use the same process, but also ask the model to always look like this from one side. And so the same approach, not only for text to 3D can also be used for image to 3D. So remember how I said like we want to make every render look more like prompt? We also can have during training like force one of the renders to look exactly like this. And so if we do this, we can get like 3D reconstructions from a single image.
But can you explain the difference between Gaussian splatting and the nerf?
Ooh, that's a different lecture. Sorry. So Gaussian splatting is also better with meshes. I can probably go here, right? Yeah. So these are generated, and this is like a mesh already.
So why we need actually nerf right now? Why not go?
That's a tough question. Let's discuss that after the lecture. Okay, so this works. This is great. Now, okay, 3D editing is something I also wanted to discuss and explain. So as I said, if we have, we can train from scratch using this prompt, and it will generate us a Lego truck. But we can also, if we already have a nerf, like a perfect nerf for this Lego truck, we can start to denoise it with a new prompt. For example, red Lego truck. And so if we do this, and for every render, it will generate us like something that looks more like this different prompt. And so if you do this, the same idea, but now we use a different prompt. It will slowly denoise, not denoise, it will slowly change the renders towards this new prompt, and therefore change this nerf towards something different. So this way you can do 3D editing with like these, the same idea, basically. And this is the idea behind this paper called Instruct Nerf to Nerf. Remember how this paper for like editing was called Instruct Space. This is Instruct Nerf to Nerf. We can do the same thing. So basically we have this data set, we reconstructed these images into this bear, and afterwards we use instruct pix to pix and instructions like turn the bear into a grizzly bear. We, using this diffusion model, we update the images to look more like the grizzly bear. And this lets us change the image. I'll show you the website.
Right, so from all the different angles, it's kind of like you do it in a different way, right? So I mean, you expect issues of consistency, or?
Yes, but the idea is that every step, every time you denoise the instructor pix to pix, you do like very little steps, so you do very little edits. And hopefully, if you have a big enough batch and a small enough edits, then they will like combine over time into something more consistent.
Mm-hmm.
This. This. This.
Well, what is here precisely like the editing or like magic, rather like it's just like a different sort of person, or is what's here stable, like the wall or like the size, shape, or what?
What do you mean by stable?
I mean these prompts are pretty different, so to say. These are all like pretty different characters.
So let me repeat. So as input, we reconstructed this guy in nerf. So we have a nerf, this guy, and then we use this procedure. We have these instructions. Then using these instructions, we slowly change every single render to look more like the instructions. For example, turn him into turn him into Albert Einstein. Then every image will slowly look more and more like Albert Einstein until the nerf itself looks like Albert Einstein.
I think the question was a large issue with morphing stuff is that like stuff is too unstable and we get like morphs all over instead of only targeted change.
Yes.
And I think we kind of saw a small targeted change in the first prompts and this demo, like when we gave him
mustache. So in practice, I think again these are somewhat very cherry-picked examples. In practice, you'll have like more issues, right? But because we use many viewpoints and we have a large batch and we have very little changes, slowly like these different changes from all these viewpoints start to aggregate into something pretty consistent.
Is there a problem that the diffusion process from different viewpoints generates significantly different results, and because of that, the model just kind of breaks?
So in practice, something that we also do is we fine-tune the diffusion model specifically on this thing. So we, using LoRa, we fine-tune the diffusion model on the images from this reconstruction.
Oh, I see.
So
Okay,
this helps us-
that way you get more consistency. Okay.
Yeah, so-
I see.
This way, our diffusion model understands more like the context, and the changes are a little bit more consistent. Okay, and there are more examples, so they're pretty cool ones. This is a practice how it works. So they do very small changes, and over time, they become more and more consistent.
Yeah, the good thing about small changes is that if you use a image generation model to make significant changes, it will hallucinate new things,
Yeah.
and from different angles it will be very different. But when you are doing small changes, it will not vary that much from different angles.
Yeah, so fair enough. So for example, this particular thing is we change him into a grizzly bear, and it's pretty clear from our viewpoint how to change him into a grizzly bear. If we ask to turn him into, I don't know, a Satan bear, then every diffusion model would have very large understanding of how to turn a bear into a Satan bear, or like a devil bear, whatever. So yeah, that's a problem. There's a next slide that will explain how we can improve on that. So there's this example. Awesome. Woo. Midnight. Woo.
Yeah, and every altered model looks worse than original.
Yeah, because
And so in this research, they use the base nerf. They just tune it on some random model that they create, or where do they get the base nerf?
the base nerf, yeah. So they
Just make something in Blender or something like that. And
no,
just...
the base nerf. I'm pretty sure this is like a nerf. They flew with a drone over this.
Oh, okay.
Land.
Okay, yeah.
You have this nerf, and then they do.
Yeah.
No, stuff like that. Grizzly bear, panda bear. These are some artifacts, so like on the head.
Oh, well, like the tail is just appearing out of nowhere.
Yeah. It's not. It's far from perfect. Of course, polar bear. And this. So these are the examples of people. And training progression is a nice skill. So like over time, this is how it changes.
So the problem is the same as it in all nerves, I think. They doesn't understand a model of lightning. So how light propagates?
Who needs that? It works. The diffusion model somewhat understands how light works, and that's enough.
But our head is understand this, and when we trying to image something, we later drawing on the paper with the light source model inside, and with some another thoughts about all of the 3D stuff. So we understand more than just pictures from the
Yeah, fair enough. So there's a lot of research going on to account for that and stuff like that.
I would maybe after this talk, I would say like how you can basically model environment, taking in account light, how it propagates. So if we do very detailed model of that in a neural network, it will generate realistic images from any angle with any light.
It doesn't. The model itself doesn't understand how light propagates.
Well,
So
but
this,
it might.
this is the reason why we have artifacts.
Yeah. Okay. Yes.
Okay, let's stop that for now. Continue.
Okay.
Let's discuss
Yeah,
this
yeah.
further.
It's,
Yeah. Also, yeah, this kind of slide is something like an improved version. This works a lot like instructor nerf, but first it works with Gaussian flagging. And sorry, like maybe afterwards, maybe in another lecture, I'll explaining how Gaussian splitting works, it's a lot like NERF, but it's like more flexible and easier to train. And what it can also do is, it can do like more control changes. For example, this interface they specify a particular region. They say that like, please generate a teddy bear on a bench here. Then in this particular region, it adds a teddy bear. And so only confined to this region, they edit. Also, like turn it into a clown. This is like a basic case.
I mean, is this NERF or is this Gauss?
This is Gaussian splitting.
Okay.
I can, after the lecture, I can explain a little bit. If you want, I'll soon make a lecture on Gaussian splitting. I actually had one like a couple months ago, half a year ago.
Oh, okay.
What it can also do is it can delete. So it does segmentation in 3D, and like you can ask it to delete something. It deletes the object. And this is it.
Тоже
So yeah, this is
Тоже
basically
осталось.
it's like the instruction alternative on steroids, where you can add masks and ask it to generate or change something in that mask specifically. Which is why, like somebody said, like how we avoid from generating random stuff all around. We can like specify a mask and ask it to generate only within that mask, which is cool. And it's a cool interface. If you have a GPU, you can try this out. It's pretty cool. But it also takes a few hours to probably optimize and change something. So yeah, the final point in this lecture is how instead of changing things with text, we might want to change something with like these intuitive dragging operations. So when you're like a 3D artist, if you want to change the position of a particular part of an object, you use a rig on top of the mesh. But if you don't have a rig, for example, you have this armadillo model, and you want to get these like natural deformations of the object, you have this algorithm called APAP. It decomposes into as rigid as possible, which basically says that we have these points, we want them to stay fixed. We have this yellow point and this yellow point here, and we move it like this. So we want this movement to look natural. There's no AI here. This is simply like some algorithms to make these deformations look natural on top of a mesh. And so again, without any AI, you can get these like pretty simple, get these deformations. But you can use this together with diffusion models to not only get these like natural looking changes in deformation, but also make them a little bit more sense in the context of like being realistic. So for example, this is an example this paper does is we have a boot. We can use APAP. It's instead of dragging just one vertex, it drags like this section with the vertex. But using stable diffusion, like the same idea with asking it to make it look more like a boot, for example, and this constraint, it will follow this constraint. Like we can move this point here, but it can also make it look more natural. And so this is an example, right? We can drag this point. It will make this smooth dragging, but it will look like this, right? But if we add stable diffusion on top, and this is like diffusion, the same process with making every render look more like a real image, then it will do this.
Are these real 3D models here?
These are meshes now.
Meshes, alright.
So to be honest, we can do all the same, not with NERFs, but with meshes. But NERFs are more flexible, so we can do we do all the texture 3D in NERFs. But in theory, we can also do it on meshes, but it's just a lot more hard. And if we do editing, we can do these edits on top of meshes, and then using like diffusion models, the same procedure that I explained, make this whole thing look even more realistic. And you can see the examples here. So if we just use APAP, this natural deformation thing, this will do this. But if we also use this paper that does scorosolation is like this whole thing, applying diffusion models onto the renders. It will make it look even more realistic. I have more examples here. Sorry. This example. We have the source mesh. We can do first stage just as rigid as possible constraints, which makes it deforms a little bit. And then after doing this whole procedure with diffusion models, it makes it look more realistic. But yeah, this works on meshes, not on nerves or Gaussian splatting. And my diploma is about making this work on Gaussian splatting. And so yeah, these are some examples. I mean, it's pretty cool. It works somehow. And yeah, so this is like my vision. So as you said, like nerves and Gaussian splatting are hard to import into Unreal Engine or Unity, but this works directly on meshes. So I think like in a few years we'll have some tools like this work on meshes in like actual production tools. Yep. Okay. Some final touches. So the honorable mentions. Let's go over them and mention some cool things. Let's not do this. Let's not do this. This is a recent model by Stability AI. Stable Diffusion is a model by Stability AI, and they recently released this thing, which is it generates 3D models just from an image. And instead of using diffusion models for this, they literally train a network that given these images, given one image, this neural network just in one forward pass generates a nerve for
So
an object.
those are nerves?
And these are nerves that are probably already converted to a mesh.
Okay.
But the idea is that, like the architecture. So they use an architecture from a different paper called LRM. So there was just this paper that made this model, but it's closed source, and it looks like this. I will not describe this in detail. I actually have a different lecture where I describe this model. Point is, we have this input image. There's this whole huge transformer, and out comes this like encoder thing that makes a nerve, basically. In comes the image, out comes the nerve. And then we can render this or convert this to a mesh. So this is like a different paper, and Stability AI made this open source. And so now, if you go to here, on GitHub, they have a link to video demo, and you can actually try this out online. Let's try this out online. So let's drag some kind of image here. Whatever you have. We need some kind of image. This. Yes, this. I just want to run this model because it's okay. It's fucking WebP. Let's do this.
How probable is it that your frog was in a data set to train it?
Fair enough, it's probable. And it's also trained on this Observerse dataset. So it's trained specifically on this. And it has like a specific style of models. It's not realistic models. It's like something that can be used in game dev or whatever. So it's a particular domain. If you feed it like a realistic image of it, I don't know, a guitar or a piano, it may not work as well. So you have to like pick out the perfect images for it. Give me not the WebP, but some actual image.
You can go, WebP is in Google. Go to the link and just get these JPEGs. WebP is open.
Yeah, it's already JPEG.
Okay, first do this. I don't know how long it will take. Okay. Okay, it loads. Let's hope it'll actually work.
So is it still processing? Or
It's processing, I think. Not sure. It takes some time, I guess.
It's Hugging Face, yes? Yeah.
It's funny, but Hugging Face is slow.
Yeah. It's very famous website.
So let's jump on to other things. Oh, okay. Let's jump on to other things for now. I hope in a few minutes it will load. Yes.
Oh.
Well, it's not perfect, but I have
multiple
examples of it.
eyes. It has multiple eyes.
It's
All
some
over
kind
the-
of shotgun you get.
Yeah. It's not perfect, but
But from one angle, it looks good.
Ну, для дальнего плана, чтобы не поворачиваться туда, да?
If we put a better image, maybe we'll experiment later. Yeah. What we also have is the description of this are. This is Igor, you said like this thing. We have this model which is just textureless. Then we apply a Diffusion model. This is a plugin for Blender. It's actually like a year-old plugin for Blender where you get a view, apply a Diffusion model, and it generates texture for you. It's not perfect, but it's pretty cool. So.
It's books in a texture.
Yes. There's also a patch of what you said about using diffusion models for new views for nerf. So you have this. So let me explain. You have nerfs, and in order for nerfs to work well, you need a lot of views. Like you need like 100 or 200 photos of a single thing. And if you use less photos, then this is what you get. But if you use diffusion models to generate new viewpoints, then you can get this. So you can help nerf learn a lot better if you use diffusion models.
So you can improve poor quality data set with this.
Yes.
Okay, cool.
Incredible.
So you firstly trained the diffusion model to understand the pictures from the data set, and then you help them understand.
Sorry.
So how does this work?
How does this work?
Yeah. So you first trained the diffusion model, and then you help the nerf to understand the data set, right?
So you have this diffusion model.
Yeah.
You using a different model, you get like this estimation of a nerf from these like very few images.
Yes.
And then into this diffusion model, you feed these renders from new viewpoints. You also feed like some encoding of this thing, so basically some additional inputs into the model, and it generates like this what it expects to be from that view. So the correction from the diffusion model, and it uses this for training.
Okay.
So it's not as trivial as I said. It uses like different models called pixel nerf that I maybe will describe afterwards, and it fine tunes the diffusion model to work well for this particular task. But it works well. So this is like there are many papers that use diffusion models to improve nerfs, but this is the one that like got the most hype. Yeah. Yes. Some more visuals. Yeah, zip nerf is like the state of art in nerfs right now, but with sufficient views. And if you use not as many views, then zip nerf performs poorly, but this allows you to make it work much better.
Is this only from 3 images here?
Oh yeah, so this is like a reconstruction from 3 images.
Okay.
If you use this vision model. And if you use zip nerf, then you get this. Let's make 6 images. Zip nerf looks like this. So yeah, this is a good visualization of the kind of artifacts you have if you don't have enough views.
Yeah.
Then 9 views. 18. 27. And all the way here.
And can you compare 3 with 81? 3 and 81.
So this is 81. This is the state of the art. This is the current paper. This is 3.
Okay. Even with 3, it looks pretty nice.
And this is, I'm pretty sure, it's not open source. Well, but maybe there's an open source version.
So we have the difference exists on with small details. If you will look again, you will understand.
Yeah, there's a difference.
There are difference actually.
So the truck is a little bit deformed here,
Yeah.
but it's still surprising how
It's incredibly good, but not
not perfect, of course. And one final thing that let's show is, remember how I showed like one of the slides? There's a pretty user-friendly tool for working with diffusion models that looks like this. It's like Comfy UI. It has lots of different nodes, and it's pretty user-friendly. And there are like there's a pack of 3D nodes. for example, you call the stability AI model that I showed to you. So, for example, they used this ComfyUI app to generate this image, and then there are a few nodes you can do just feed it into this 3D model, like triple SR, and out comes the mesh. So this is like a pretty user-friendly to use these models, user-friendly way to use these models. Or this, or this. This is like a pack of pretty good 3D neural network models. What does this do?
This kind of this thing can make you depressed. I think it's so cool. It's incredible.
Yes.
Is it also comfy what?
ComfyUI, yes. So this is the repository for the 3D pack. There should be a link to.
Does it run locally?
Yes, it runs locally. But you can. What I do when I do experiments with GPUs, I rent a server on with a GPU, and I run these apps there. And I can just connect to the server and I have a GPU, but it's too bad for these diffusion experiments. So I rent a GPU on a server, connect there, and do the experiment there. Okay, and I'm pretty sure this is all I want to show. Yep. Thanks for listening.